All right, in this video, we are going to look at a little bit more advanced case of depreciation, and specifically this concept that is thrown around often, being underwater on debt. I'm going to specifically state what exactly this means. So we've already introduced depreciation as something that's unusual as a result of timing differences between economic value and cash flows. The idea is that it separates cash from an economic reality, and that is the wear and tear on a particular asset. In this example, we'll use a car so that it's aligned with examples that I've used in other videos. So now we're going to take this more advanced step, one that better matches how assets actually behave in the real world. Because most assets don't lose value in a straight line, as I mentioned in the introductory video. They lose value faster at the beginning. And that takes us to what's called exponential decay, and ultimately to a very real financial problem, which is being underwater, or the difference between what an asset is worth and the value that's remaining on a loan balance. So let's do a quick recap. No cash, but real costs. So depreciation is not a payment. There's no cash flow. No cash leaves your account, and depreciation, when depreciation rather, is recorded. So instead, it reflects that something you own is losing value over time. So cash is what was paid for the asset, whether you got a loan first to get the cash to then pay, or whether you paid for it in cash completely from cash reserves. But depreciation is what is used up. The original purchase is just converting cash into another form of asset. And we need to record the economic value consumed over time. So we want to move beyond straight line, and straight line depreciation assumes an equal value loss each period. And it's simple, but it's often unrealistic. So if we think about a car, there's usually a big drop early in the value as soon as you drive it off the lot. And then there's smaller drops later on. So that's not a straight line, that's a curve. And that curve is captured using exponential decay. So I'm going to share my screen as usual, and we're going to get into just a comparison of this depreciation method. So here we go. All right, so on the screen, you can see in the past video, and again, I'd encourage you to look at that to get caught up. The cost was 30, the salvage value was 5,000, the depreciation base was 25, and the time was 60. That created the straight line depreciation schedule, where the depreciation expense was $416.67 for the entire period, 60 months. We then moved on to units of production. We said, okay, let's not focus on time as the factor that determines the depreciation. Let's look at the actual usage. So we said, okay, the cost is still 30, the salvage value is 5, the depreciation base is 25,000. Now we have an expected usage life of 200,000 kilometers, and so we have a depreciation rate, which is the 0.125 or 12.5 cents per kilometer driven. We then looked at how many kilometers were driven, and we got our depreciation expense, which changed based on that activity. So now we want to get into this accelerated exponential decay. The cost is the same, the salvage value is the same, and the useful life in months is the same. What we want to do is we want to use this equation, which is the exponential decay equation, to be able to find out how much depreciation is more realistic, so that there's a bigger drop in the early months and lesser in the future months. We also want to make sure that mathematically we arrive at that 5,000 salvage value. Now, the way that we do that is we use this formula. The future value is equal to the present value times 1 minus r raised to the power of t. Okay, where the cost here is our present value, The salvage value is our future value. The useful life is 60 months, and we need to solve for R. So we need to isolate R there. So I'm going to go through a number of steps. I had the answer there, but we'll go through a number of steps here. And we'll populate the answer back up here. So if we take the future value is equal to the present value amount, if we divide both sides of the equation by present value, then the first part of this equation is future value of 5,000 divided by the original cost, okay? So that removes the present value from both sides. Okay, we divide, or removes it from the right side, we divide by present value for both. So now we have to deal with this 1 minus r raised to the t. Well, the way that we get that raised to the t out of the right-hand side, again, we're trying to isolate r, is we have to raise both sides of the equation to the exponent 1 divided by 60, okay? Because that time would be 60, so we have to isolate it and remove it. So we raise this to the power of 1 over 60, and that's going to eliminate the power. Okay, so now what we have on the right side would be 1 minus r, okay, and everything else is on the left side. So how do we get rid of that 1 minus r? Well, we subtract 1 from each side, okay? That's going to leave us with minus r, and then we have to multiply the entire equation by -1. So we put a bracket here, a bracket here, and we can just put a negative sign here, okay? And that gives us 0.0294. So this is the rate that we want to use. I'm just going to copy this and I'm going to paste it here. So the next step, we want to create the exponential decay depreciation schedule. Now, I've already done this, but I'll walk through the steps so that you have clarity. We've got our 30,000 here. Our depreciation expense is just going to be equal to our value, our beginning value, multiplied by this depreciation rate, okay? But we want to keep that anchored, so we're going to put dollar signs before the B and dollar signs before the 18. That gives us a depreciation expense in month 1 of 882. Okay, now think about this. It's like you walking off the lot with your car. You just lost a significant amount of value, which is more like reality. Accumulated depreciation, we'll just keep track of this as we go. And the ending value is just the beginning value minus the depreciation expense. That ending value becomes the beginning value of month 2. We apply the depreciation rate, again, from the depreciation inputs tab. We get a smaller depreciation expense, our accumulated, our ending value, and so on and so forth. So once we get to this line here, we can just literally pull this all the way down. And to make sure that everything adds up, this value here should be equal to the 5,000, which is the salvage value, okay? So that is the accelerated exponential decay bit. Yes, working with the formula to calculate the rate is going to be the most challenging, but if you're pretty decent at math, I think that was covered probably in grade 9 or 10, at least up in Canada, maybe even before that, then you're going to be fine. So this concept of underwater, we need to look at the amortization schedule. And again, I'm not going to go through the entire process of how to build an amortization schedule there. There is another video for that. But essentially, you want to see how the loan changes over time. So we've got the $30,000 loan that we used to take out to buy the car. The interest rate here, we're assuming, is 8%. And we have to put it in monthly terms, so we divide it by 12. That gives us the 0.0066, et cetera. And the term is for 60 months. So we've got our beginning balance, the interest, which is just the beginning balance times the interest rate, our payment, which again, in that other video, we use the payment formula and I describe it there, but you just put the payment in. The difference between the payment and what goes toward interest, which is really the true cost of borrowed money, is the principal, and the portion that goes toward the principal, and the ending balance is the difference between the beginning balance and the principal. Okay, so that becomes our beginning value, and so on and so forth. You can see that the interest, the cost of the interest, goes down throughout time, and this ending balance is what's remaining, the balance that's outstanding of the loan. So we need these two pieces of data. We need to know the ending value of the asset itself, okay, which is this ending value here. And we need to know the ending value of the loan, which is this value here. So assuming that we have these, we have our months, the net book value, which is essentially the value of the asset over time, the balance owing, which is the value from the loan, and the delta, I'll explain that in a second. What we want to do is we want to create a graph so that we can see a graphical representation of how the depreciation or the value of the asset changes over time, and compare that to the balance owing on the debt over time. So the way that you do this is you select these three columns, which have the months, the net book, and the balance owing. And you want to insert the scatter diagram. Okay, this will give you pairs of values. So for month one, the net book value will be the 29,117, and the balance owing will be 29,591. So if we do that, it'll show us for each of these. Okay, so I'm gonna, if I can, I'm going to move the chart to its own sheet. It looks like I have to create the sheet first. So let's do that, sheet one. And then we're gonna move this, move chart to sheet one. Okay, and I'm just gonna make that a little bit bigger so you can see. So what we're looking at here is the asset value, which is the blue dots, compared to the loan value, which is these orange dots. And you can see being underwater means that your asset value, the blue dots, is less than the amount that's owing the red dots. Okay, so this is a graphical representation of what it means to be underwater. Obviously, there's a maximum point of being underwater here, and out of curiosity, I wanted to find what that was. So I calculated the delta, which is just the difference between the balance owing and the net book or the asset value. Essentially, if you calculate that and then just run the numbers all the way down, you'll hit a maximum value. And you can just use this equation equals max and then select all of the data to find out what that maximum value is, which is 4807. And that happens right here. Okay. So this is the maximum underwater scenario given the exponential decay and given the amortization schedule. Okay. So 4807. So at month 22, that is the worst case scenario under the assumption that you have a loan for 30,000 at 8% annual percentage rate, 60 months, and you're using the exponential formula to be able to depreciate the asset in a more realistic way than straight line or units of production. Okay, I hope this has been helpful, has provided you with some insight around being underwater and the risks that are involved there. If you like, be sure to like. If you'd like to see more content like this, hit subscribe, and I'll see you in another video.